and currently I am also a student council for this year. Today is really an honor day for me to be an MC, and this is really my pleasure to have all of you here with us, as well as we have Mr. Hengjimmy Song, who is from CS department as our guest speaker for today, and he will respond into the topic about stress detection. Anyway, if you guys have any questions, please don't be hesitate to drop them in the chat box or we enter the Q&A session. And if you guys can unmute yourself, it would be better. So please welcome Mr. Hengjimmy Song for your speech, for the introduction and the explanation as well. Please.
Thank you, Wong, for the introduction. So yes, just as a background information, I am Hengjimmy Song. I am a senior student from the MIS department, and my final year project that I'm presenting about today is stress detection. So I will start sharing my screen and get on with the presentation. Okay, everyone can see my screen, right?
Yes.
Okay, so as I mentioned, my project is stress detection. It's under the course of final year project, as final year project, supervised by Dr. Marambek. And also my mentor for this project is Mr. Li Heng, who's a senior AI developer at Prudential and also one of the instructors here in our university. So starting off, we will go through the table of contents. We have 8 main points that we're going to cover today. We have introduction, related work, pre-processing, methodology, output, varieties, interface, and demo. Now starting with the first one, which is introduction. So in the introduction, we will discuss, the first question is why detect stress? So what encourages me and inspire me to do this project in the first place? So as we know that depression is a real thing, psychiatrists around the world is trying to fix this problem because depression rates are rising globally as we speak. Currently, there's more than 264 million people who show depressive symptoms globally. And also locally, we see a spike rise in number of depression, especially during the COVID pandemic, where everyone has to change their lifestyle to adapt to this new situation. Secondly, we are detecting stress and not depression itself because stress is more common than depression, but there is no doubt that stress is also a major factor that causes depression. So we're starting off with stress because it's one of the specific traits that causes depression. So it helps us to detect depression for an early diagnosis. What does an early diagnosis give benefit for? So early diagnosis also increases the chance of successful treatment, meaning that if depressive symptoms are treated as soon as possible, there's more chances that it is cured permanently and temporarily. Depressive symptoms that are delayed in terms of diagnosis is harder to cure. That is proven by many psychiatrists who prefer to talk to people when they start falling into depression rather than people who's already in depression. Now, in order to understand the entire project, we also need to understand the project goals. So my goal into creating this project or deep learning platform is to make it easy and accessible anytime, anywhere, meaning that with just a push of a button and a few seconds of your time, you can check whether or not you're currently stressed or not. And if you're stressed for a lot of time, a lot of percentage of the day, that means that you may have some depressive symptoms and you should seek some help. And the accuracy that we're aiming for is about 70%. And we're trying to base off our prediction based on the user's voice only, meaning that we're going to look at their voice, their pattern, their pauses, and even some of their breathing sound. And lastly, one of the main goals of this project is also for me to explore into the deep learning field because it's one of the fields that I've always been interested in, but did not have the time. So it was a great opportunity to really learn something new. Now, before we start off with our own work, we have to look at some others work globally by researchers and students and see how we compare as well. So starting off in 2018, uh, 3 students from Hong Kong University researched on this, and they actually made something as well. So instead of focusing on the tone and patterns within the voice, they focus actually on the speech recognition. So it's more of using deep learning in order to identify the words that they're saying, and using the context of the word, it allows it allows the algorithm to predict whether they're stressed or not, and it has up to 74.1% accuracy, and the main algorithm used is long short-term memory. The thing to note here is that because this is trained on speech recognition, it's not universally usable amongst all the languages because it relies on the content of what they answer to certain questions. So it's really highly based on which language they train it on. In this case, they train it on English. There's also some follow-up study that tested this theory on Chinese, but I was not able to include the paper here. Secondly, this is very recent in March 2020. The approach is a bit different. They sacrifice accessibility and ease of use, but it really bumps up the accuracy to a very high level, which is 94.33% accuracy. How did they achieve this? Is that they look for ultra short pulses. It's when your heart beats on a very short pulse and quite rapidly. And how they achieve this is that they use a heart monitor, the thing that you clip on the finger for patients in the hospital, and using data from that, they can use support vector machine in order to predict with such accuracy. Now, after we understand all of our sort of competitors, it's time to explain our own process. So before any or convolutional neural network project gets started, there's a lot of pre-processing that goes. If anything, pre-processing actually takes more time than developing the product itself. So first step is data collection. In this case, I had to create a small application where I can record the user's voice while letting them answer a few selected questions when discussed with Ms. Chita, who has some background in mental illnesses, and she knows the right question to ask. And at the same time, there's a quick survey for the end. The quick survey will not be there in the final product during the data collection. It's only there because having this survey helps us label them easier, meaning that initially our algorithm will not be able to know which voice is stressed and which voice is not. So the survey gives us a very good labeling support, so that we know that the data we collected, whether that person is stressed or not during the interview. Secondly, since we're working with sound, I have to do a quick explanation between sound and images. So sound is a linear data that is one-dimensional, and it is sequential, meaning that it's an array of numbers that's in a one by a certain length of the data itself. So this is a sequential data, while a Mel spectrogram, which you can see in the picture earlier, it uses a picture to identify sound waves. It's three-dimensional, meaning that it's two-dimensional in the size of the picture, which is the width and the height, while also having a depth of 3, because colored pictures are made with a combination of three core colors, which is red, green, and blue. So why did I choose Merle spectrogram? Because based on many researchers and studies, and also advice from the mentor, it's not wise to train on raw audio itself due to the complexity that it produces during training. This also, when using Mel spectrogram, it gives us an advantage is that Mel spectrogram, unlike audio sound waves, it doesn't only give priority to the highest amplitude of sound. It actually gives priority to all frequency uh, that exists within the audio file itself. And lastly, as mentioned, we're using convolutional neural network, which is mainly an image processing algorithm, and it's not really good for sequential data. So we are fitting our inputs so it better fit into our convolutional neural network. Now that we understand the pre-processing stage, we can now look at the methodology itself. So starting off, what is convolutional neural network? So convolutional neural network is an artificial neural network that is used quite frequently in most, if not all, cases of image recognition and processing that is specifically designed to process pixel data. As mentioned, like a picture of the Mel spectrogram, we're converting all of those into numbers that have a matrix of the width, the height of the image, and also a depth of 3, which is the color. If it is grayscale, it's only a matrix of 2 dimension. Our main algorithm or powerhouse of this project itself is VGG19. This is this is one of the variant of the VGG model, which consists of 19 layers. So in this case, it has 10 convolutional layers. There's a typing error there. 3 fully connected layers, 5 max pool layer, and 1 softmax layer. This algorithm, we're using the library from TensorFlow, which is also a well-known platform for building many deep learning projects. The weight of this algorithm, we're using ImageNet as the weight because ImageNet has proven itself in helping many students and researchers in the field of image and vision research. It's basically a catalog of 14 million images that's organized according to the WorldNet hierarchy. So this is the structure of the VGG19. As you can see, there's a total of 19 layers, and we're only using the first 15. Why? Because we're trying to reshape the output ourselves. So we're using the step from the 224 by 224, which is the size of the image that we're importing, and 3 for the 3 different channels for colors. And we're only reaching this red box point, which is the last max pool that we're using, which is 7 by 7 by 512. So in order to understand this, we need to look at the 2 different layers that we're using from VGG, which is convolution layer and max pooling. So as a brief explanation, convolution, what it does is that it has a filter, an input, and a result. So as you can see here, the input, there's many calculations within the filter, and then you get an output on the final matrix that is the result. In this case, it's shrinking down a 6 by 6 by 3 using a 3 by 3 by 3 filter, and it's able to output a 4 by 1 matrix. But in our case, it's a bit different because we're adding empty pixel around the edges so that we get the same matrix. We're not trying to shrink down the size of the matrix. We're just putting it through all the filters. So this is a brief summary back into convolution. As you can see that the depth, which is regarded by the number of filters. So as we add more filters, the depth of the matrix always increases from 64 to 128 to 56. And lastly, 512. Another layer, which is max pooling. Max pooling is a lot simpler. All you have to know is how much time are you trying to shrink down the matrix itself. So in this case, it's a 4 by 4 into a 2 by 2. So as you can see, the pixel that is colored max full, all it does is that within the input range of 2 by 2, it just pick out the maximum number and place it in the new matrix. So in this case, it's 20, 112, 30, and 37. So as mentioned, we are not using the last 4 layers of VGG. So we're doing the last 4 ourselves. So we're using global average pooling 2D, fully connected using activation function of ReLU, a dropout of 30%, and another fully connected layer that uses softmax as the activation function. So global average pooling, as mentioned in VGG 19, in the last layer, it's 7 by 7 by 512. So in this case, we're shrinking it down to 1 by 1 by 512. So in the 7 by 7 matrix within each layer, we're summing it up together to get a number and dividing by 49, which is the number of pixels. So we're shrinking down all those numbers into a 1 by 1 by 512. In this case, we're turning it into a one-dimensional data where it's only in one line. So after making it into one line of 512 nodes, we're using the first fully connected layer in order to shrink the number from 512 down to 64. Fully connected, how it works is simply there's a hidden layer where there's a lot of math and calculation regarding the bias and the weight itself. And the bias and the weight defines how much it affects the end product. So this is all automated in itself. We just have to decide the right activation function and the right number of nodes in the input and in the output layer. So as mentioned, fully connected layer have we are using 2 activation functions, which is softmax and ReLU. In this case, softmax, it's within a certain threshold, it's shrinking the data into this curve. Why it's very complicated in math, but in a sense, it's proven itself in many deep learning algorithms, and it's quietly used in a lot of places. This, in a sense, is just it amplifies. But if the number is higher, it amplifies its weight regarding to the final product. It's trying to make a difference and make the node that matters more matter a lot more, and the nodes that doesn't matter less. So it's trying to eliminate the less useful ones and keeping the very useful ones. And we also have ReLU, another type of activation function. In this case, ReLU is quite simple. Anything that is below a certain threshold is dropped to 0, meaning that if a node has a weight of, let's say, less than 0.5, we're dropping it out because we don't want to use any nodes that's below there. One of the layers, last type of layer that we used was dropout. So as explained, fully connected layers, there's a lot of connection between a lot of the nodes within each stage. But in this case, we're randomly eliminating 30% of the nodes in order to prevent overfitting. What does this mean? It means that we are trying to tell the algorithm not to rely too heavily on any specific nodes, as it may overfit to a certain data, and when we include new data, it might not be able to predict it with accuracy. So this is the model summary of the project itself. So the picture that we're importing is 224 pixel by 224 pixel, and it has 3 channels, red, green, and blue. So this is the shape of the matrix. After the first 15 layers of VGG, we get the 7 by 7 by 512. And after global average pooling, we're reducing it to 1 by 1 by 512. In this case, it's becoming linear data, so we can just focus on the depth. So in the first fully connected layer that uses ReLU as the activation function, we're reducing the node from 512 into 64. In this case, we get over 32,000 parameter changes because if we connect all the nodes in a sort of as you can see, the lines cross from each input node to all output nodes. So in this case, it's 512 times 64 plus 64, and we get this number. And drop out, we're keeping the same number here. We're just dropping the 30% of hidden layer nodes in order to prevent overfitting. And lastly, in the last fully connected layer, which is softmax, we're reducing 64 to 3. And again, we get 195 parameter change because it's 64 times 3 and plus 3. So after all that's said and done, what does our algorithm output? So when we give it a MERS spectrogram of a sound wave of a human voice, it will give us this output, which is an array of 3 numbers. So this is the probability that it is index 0, index 1, and index 2. In this case, index 0 is highly dominant, and during the training process, here's how we label it. Index 0 is not stressed, index 1 is stressed, and index 2 is highly stressed. So in this case, for this specific prediction, it's identified that the person is not stressed. So we can look at the varieties in the process, because in any deep learning project, it's not a one-shot deal. There's a lot of tweaking and parameter changes that has to be done in order to increase the efficiency. So these are some of the examples of the different parameters that was used in the making of the algorithm. As you can see, we didn't really start off with VGG19. We started off with VGG16, but it was not performing well, so we tried VGG19. And once we get some improvement, VGG19 was the core algorithm for a few months during the entire year of the project, but in the final stages of improvements, it's found out that the last 4 layers of VGG19 is not that useful for our case, so we are eliminating it, and we are doing the reshaping ourselves, which bumped the accuracy by almost 7%. Lastly, that was just building of the algorithm. We also need an interface for the user to interact to. So in this case, we're using Expo, which is an open source platform that's used for making universal mobile application for Android and iOS, and also web with just one code, meaning that I only have to write the code one time. It can be used on all of these platforms. In this case, we're only using the Android and iOS platform. Secondly, since our algorithm is done in Python, we are using Flash as our backend or server. Flash is basically a Python-based micro web framework. The keyword here is micro web framework, meaning that you can include different libraries for different functions. And in this case, we're only using core Flash function, so we only have to install a small amount of library, and it's quite simple to implement. In the last part of my presentation, I would like to show you a demonstration of the application itself. So I will be testing it from my mobile phone. Yes. As you can see on my phone screen, there's a 2 simple button, which is start and stop. I will just record the voice quickly and get an output. So as you can see, the context of the voice doesn't really matter. It's most basically on your talking pattern. So meaning that even though I'm trying to detect my stress at the moment, it's really not important what I'm saying, that I can just talk to you guys on this presentation, and it can give me a prediction. So the output is not stress. This is the simple output that is on the UI. I can show you the exact prediction because currently the backend is run on my computer locally. I'm sending the output into the chat. So in that specific prediction. It was 70% confident that I was not stressed, 28% confident that I was stressed, and less than 1% saying that I was highly stressed. So in conclusion, I was not stressed at the moment. So the output is very confident that I'm not stressed. That is it for my demo and presentation. If you have any question, please feel free to ask.
Um, Thank you for your splendid explanation and like the whole speech, because I have known what I've never I've never thought that I might want to know all of those things. So thank you so much. And if anyone have any question, please feel free to ask our speaker. So there's a question from Nathan. He asked, does it work for any language?
In a nutshell, yes, but it will also require a lot more training data because I was collecting the data for myself there, so there was not as much training data that we hoped for, but it should work on most languages. The only downfall on the algorithm itself is only if a language have a very specific accent or a very specific speed of talking. So it might take some time for the algorithm to adapt. And keep in mind that the algorithm itself, if people are using it, it's actually training more on itself. So the more people who use it, the more accuracy it gives. So it's only a matter of time before the algorithm is able to predict and not be limited to any language. But currently, it's limited to a very strictly different accent of language. In this case, Khmer and English works fine, but something, let's say, for example, German, it has a very deep tone, so it affects the algorithm itself.
Oh, there's another question from Chai. He asked, what is the minimum data set to provide in order to use high accuracy?
Yeah, so in deep learning, there's no right or wrong or yes or no answer, but in this case, I can give you my example. My total data set was around there were like 4,700 training data and also 200 uh, 2,000 validation data. Keep in mind that each interview actually offers us more than one data because each mass spectrogram only support 5 seconds of the user's voice. So we are splitting all of it up and creating multiple data. So on average, a 10-minute interview can give us up to 120 data points. So in this case, what I originally aimed for was 10K data set, but unfortunately, we were only able to get to the 6 and 7,000 mark. But yeah, in deep learning, there's no yes or no question. It's more on each use case and each prediction and the different algorithm that you choose in the process. Because as you can see, even in my case, there's a lot of changes during the development phase from changing the core algorithm and changing the many different reshaping layers and many parameters that was tweaked in the process. What you saw in the presentation was just a summary in the variety. It was just a summary on all the trial and error. In my case, there were around up to 50 automated models that were generated. The model is what you use to predict in the last place. But for the manual ones, there's only up to 10 because training actually takes a lot of time. Each version takes around one whole day to train. So yeah, there's no certain answer on minimum data set. It's more on what you're trying to train on. If it's something that's easy to predict, it won't require as much data. It can go as low as hundreds of data points. But if you're trying to train something that has a lot of varieties, especially in our case, which is voice. Example, you're recording your voice in front of a fan. It might cause a lot of disturbance, and the algorithm also have to adapt to it, and in order to improve its own accuracy. So yeah, that is a case by case basis.
Thank you for your questions and as well as the answers from our speaker. So, do you guys have any more questions want to ask our speaker? I guess no, right? Okay, so this is the end of our session now. So, may I have a group photo before we end the session? It would be better if you guys open your camera so that we can have a group photo. Okay, so I will count 1, 2, 3. Okay, thank you so much. Thank you so much for your speech. I really appreciate your hardworking just to sharing us today, and I hope that I can see all of this topic, all of this thing in the future. Okay, more moreover, I also give my appreciation to the audience for spending your valuable time with us for today. On behalf of ICT faculty, I would like to give my I would like to ask for my for the forgiveness if I have made any mistake during the session. Anyway, we still have another session in the after this session ends, so please don't forget to check out our website to find out and to join with us. So see you guys later in the next session. Thank you for your presence. Bye bye, have a nice day.